Hello, everyone. Thank you for coming to my fourth talk, and this is on the anthropic principle. For those who have not watched my previous talks, you're welcome to go back and watch those. But just a brief introduction, my name is Dr. Christina Sweeney-Hillesheim. I have a doctorate in chemistry and a master's of divinity in apologetics. And so we're going to look at the anthropic principle. So you might say, well, what is the anthropic principle? You're not really sure like what that word means. So this is derived from the Greek word anthropos, which kind of stands for man. And this was coined by Cambridge physicist Brandon Carter. And so another way that people kind of think of the anthropic principle that might be more commonly, something you more commonly heard, is the fine-tuning principle. And so you might say, okay, well, but then why is it anthropos and man if it's like the fine-tuning principle? Where does man come into play? So, kind of the definition of the anthropic principle is that all the seemingly arbitrary and unrelated constants in physics have one strange thing in common. These are precisely the values you need if you want to have a universe capable of producing life. So, the idea here with anthropos or the anthropic principle is that this is the principle as to why we have life in the universe. So why are we able to have life kind of from the standpoint of looking at the different physics principles, laws, and constants that are in our universe. So essentially, the challenge of this principle was summarized by Alistair McGrath in two kind of questions or points. Is it a pure coincidence that the laws of nature are such that life is possible? And might this not be an important clue to the nature and destiny of humanity? So, those are the things that we want to look at with the anthropic principle. Is this pure coincidence that the laws of nature are fine tuned? And what does that mean in relationship to humanity? So, who noticed this fine tuning first? So, a few people kind of saw aspects of it, but the first person to really kind of say something in regards to this is Sir Frederick Hoyle, about in the late 1950s. So he noticed the precise process by which carbon and oxygen are produced in a certain ratio inside stars. And one thing he was noticing with this ratio is if you were to tinker with the resonant states of carbon or even this ratio, you wouldn't get the materials needed for building life. Now, this is important because we get certain elements from the life and death of stars. So looking at what stars are producing is going to be important to look at how life is able to exist and this fine tuning of the universe. Now, not until the early 1980s was most of the research and writing taking place. So kind of 1950s, we start to see this, but it takes about 30 years before people start really looking at it and started writing and researching this area. A little bit more about stars. Heinz Oberhummer, who is a physicist, he noticed a very important kind of value. So the strong nuclear force, this is the force that binds protons and neutrons in the nuclei. So in the atom, you have the protons and neutrons in the middle in the nuclei, and the electrons are surrounding them. And so this is that strong nuclear force that keeps the protons and neutrons here. Because if you have electrons outside, electrons outside, and protons inside, you might say, well, why don't the protons just like leave to go to the electrons? And so the strong nuclear force is what's kind of keeping them there with the neutrons. But what Heinz Oberhummer noticed, is that a 1% change in this force would have a 30 to about 1,000-fold impact on the production of oxygen and carbon in stars. Now you might say, okay, so the amount of oxygen and carbon produced in the stars has changed, but what does that really matter? Well, stars provide the carbon and oxygen needed for life on planets. So if that changed, then our conditions for life to exist in the universe would not be optimal. Right now it's optimal, and if we just tweak that strong nuclear force just a little bit, then that directly affects oxygen and carbon production, which then directly affects the conditions needed for life. And so this is one of the things that he noticed and he wrote about. Now you might say, well, why is all this important? What is the idea of this? Okay, so you've got one example here, you've got one example here of things that are fine-tuned. But how does that really relate to maybe an argument for the existence of some sort of designer? Where do we get design from this? So I want to give you kind of an analogy. So think of like a biosphere. So there was one that was built in Arizona a while back, if you're familiar with that. But if not, here's kind of a mock image of a biosphere. So think about biosphere is just kind of like a big domed area, kind of on Mars or on a planet that allows for its own eco environment inside. So imagine astronauts land on Mars and they find this enclosed biosphere, this little sort of dome structure that you can kind of see in the picture here. And when they go in, they go to like the control room and they find a panel, big control panel. There's got a bunch of dials that are kind of controlling the environment for this ecosystem. And they're set perfectly for life. So this dial is like the oxygen dial and it's set perfectly the right amount of oxygen that's needed. This is the temperature dial, 70 degrees Fahrenheit, 21 Celsius, humidity is 50%. And then they notice there's a whole system for replenishing the air to keep it fresh, systems for producing food, generating energy, and disposing of waste. So they notice, these astronauts notice this entire kind of control panel with all these precisely dialed in knobs. Kind of maybe something like this picture. Now, each dial has a huge range of possible settings. And if you were to just adjust one of them or more of them just a little bit, like just go boop over one way or another, the environment would go out of whack and life would not be possible. So if you were to go in and you would notice this, maybe you went in and you tweaked one of the dials, then would you see and you saw that the life in the environment did not exist anymore? What conclusion would you draw from that? Would you just walk in and see that it was all arranged very specifically and go, oh, this is perfect? It must have just happened this way. Or would you conclude that somebody must have came in and taken a lot of time to kind of adjust all these dials so that we would have this biosphere and have perfect life? You most likely would have that second conclusion, that it was designed and somebody took great care in kind of tweaking it so that biosphere would be prepared and be ready for life. So there, in this case, in our universe, you can think of our universe as kind of that biosphere. And we actually have more than 30 separate physical or cosmological parameters that actually require that precise calibration in order to produce a life-sustaining universe. So you can almost think about our universe has its own little control panel, and we have multiple different dials that are turned just to the exact location they need to be for life to exist. So I'm just going to talk about 5 of those dials, which are kind of the more common ones or more interesting ones based on the level of precision that they require to have. So the first one is one that you might be more familiar with. That's kind of the more relatable one, which is gravity. Then we'll talk about the cosmological constant, the mass difference in neutrons and protons, the strong nuclear force, which is what I mentioned earlier with Heinz, and then the original phase space volume. So let's talk about gravity. And so this analogy was written about by Robin Collins. And so if we want to think about gravity and we want to kind of understand its strength and how it relates to the other constants, I want you to imagine a ruler that goes all the way across the universe. So a really, really, really long ruler. So we have a ruler that's going across the universe and it's broken down into 1-inch increments. So, or if you like, 2.54 centimeters. So if we're doing this, breaking it down, and it's across the entire universe, there's going to be billions upon billions upon billions of inches because the ruler is really long. So we've got a lot of inches. Now imagine that the entire ruler represents the range of strengths that we can have for these different like gravity forces, all these different forces that we're going to talk about. So you'll have the weakest ones on one side, you'll have the strongest ones on the opposite side. Now, gravity being the weakest force, is going to be over here on this side. And the strong nuclear force that binds those protons and neutrons together would be over here on the opposite side. So we'll talk about kind of two very different strength forces in this talk. So gravity on one, strong nuclear force on the other. So the strong nuclear force actually ends up being 10,000 billion times stronger than gravity. So it's 4 billions. That wasn't a typo. So it's very much stronger than gravity. So that kind of gives you an idea of this range of how much stronger the strong nuclear force is in relationship to gravity. Now, the range of the possible settings for the force of gravity can plausibly be taken anywhere in this whole length of the ruler. So even though we know that gravity is all the way over on this end because it's the weakest, theoretically, gravity could be possibly anywhere on this scale. So now what we can do is we can think about, well, what if it moved on this scale? What would we expect? So what if you move gravity on the scale? Now, you might say, okay, if I move it all the way to the other side, like you expect a lot of big changes. But let's not be super drastic like that. How about we only move gravity on this scale by 1 inch? So we're just going to move it just a little bit. But remember, this is over the universe. So if I move it by 1 inch, then this is actually a billion-fold increase in the strength of the force of gravity. Now, you might say a billion-fold increase, that's a lot, but it's actually really, really small compared to the length of the entire ruler. So remember, the length of the ruler is really, really low. And if you imagine, put it on the screen, like if this is the length of the ruler and I moved gravity, I'm only kind of moving it like this much, like just a very little bit into the whole grand scheme of the ruler. So the amount that we're actually moving is going to be 1 part in 10,000 billion. So 3 billions. So it's a very small amount that it's increasing, even though it is increasing a billionfold. So what would then happen if we increased gravity by just this little 1 inch movement on our scale? Then what would we expect to see? Well, animals anywhere near the size of us, or anything, pretty much anything bigger than a bug, would not be able to exist. It would be crushed under just the force of gravity. And then insects, they would only be able to survive, but they would need really, really thick legs to be able to support themselves. So imagine kind of like elephant legs on some of these like little bugs. So they would need very large legs just to be able to support themselves underneath the weight and force of gravity. Now, this is if we were to increase gravity by a billionfold. What if I were to increase it only 1,000, just 1,000 times stronger? So if that were the case, what would happen is Earth would end up having a diameter of only 40 feet. So imagine that. Our Earth now, because of gravity and the effect of that, would be only a diameter of 40 feet. So it'd be very, very small, meaning it wouldn't be able to sustain life on it because you would not have all the factors that you would need. Another thing, say if gravity was 3,000 times stronger. So stars that have lifetimes of more than 1 billion years, so any star that, is going to live more than 1 billion years, wouldn't exist. And to give you kind of an idea of like, well, I don't know how long stars live, our sun has got a lifetime of about 10 billion years. So if our sun is 10 billion, that would mean that if gravity was only 3,000 times stronger, our sun just wouldn't exist. No sun, no life. So this just kind of gives you an idea of just the effect of just tweaking gravity. If we tweak it even just 1,000 times stronger in that big scale of all the possibilities of how it would affect life. So it's very, very fine-tuned for life to be able to exist. So let's talk about our second law, our second constant. So this is the cosmological constant. And so the cosmological constant is kind of the amount of energy in empty space. And so this is part of Einstein's equation for general relativity. And so if you look down here, this is, and highlighted here is that space for the constant. Now, this constant, in theory, could have any value, a really big value, a really small value. It could be positive or it can be negative. But if we're thinking about it and we wanted to try to guess, we might assume that this constant would be very large because space is really large. There's a lot of empty space in our universe. And so we might think, okay, well, this must be a very large positive number. So if this were a very large positive number, then what would happen is the cosmological constant would act as a repulsive force that increases with distance. So what does that mean? So if it's a repulsive force, then anything that would be coming closer together, it would then not want to come closer together. So what we have is at the beginning, after the Big Bang, we started to have this clumping together of our galaxies, of matter, so that we would have galaxies, stars, planets, and everything. But if this constant was large and positive, then this would prevent any of that clumping together. So no galaxies, no stars, no planets, nothing would exist. Okay, so maybe it's still large, but maybe it's negative. Maybe it's one of those weird ones where it's negative, even though we think it might be positive, kind of things. Well, if it were large or negative, then the cosmological constant would act as an attractive force that increases with distance. So this would immediately reverse the expansion of the universe. So right now we understand that our universe is expanding. So at the Big Bang, the initial expansion, and then it's continuing to expand. But if this cosmological constant were large and negative, then it wouldn't be expanding. It would actually reverse the expansion of the universe and cause it to recollapse, which is not what we see. And then we wouldn't have universe. So then that kind of says, okay, so it can't be large, can't be a large number. So let's continue to look at it. So however, our astronomical observations show the cosmological constant is actually quite small. It's a very, very small number. The precision of the constant has been estimated to be at least 1 part in 100 million, billion, 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 billion. So to kind of give you an idea, that is 10 followed by 53 zeros. Now that might be a little difficult for you to imagine the precision, like 53 zeros. You can kind of like picture them, but that's hard to how precise that is. So to give you an idea of how precise that is, this would be like hitting a bullseye. So you can either think about it like with my picture here with a dart or a bow and arrow. So trying to hit the middle of the target. That is 1/1,000,000,000 of a trillionth of an inch in diameter. So even trying to hit a regular bullseye is hard. But think about trying to hit something that's less than the size of one atom. We can't even see that. So you're not going to be able to hit it. So that just kind of gives you an idea of the level of precision of the cosmological constant. So let's talk about the third example. So this is the mass difference between neutrons and protons. So the mass difference between neutrons and protons, if we were to change this, increase the mass of the neutron by about 1 part in 700. So just a very small change, a small increase in the mass of the neutron, then nuclear fusion in stars would stop. And you might say, well, what does that matter? We need nuclear fusion to happen because then we need to have, like we said before, with the strong nuclear force, with carbon, with oxygen, we need stars to be able to, die and be able to have all those elements and things be created. If nuclear fusion in stars would stop, then we're not going to have the materials we need for life. No energy source and none of the other materials are needed. The next one is the strong nuclear force that we were kind of talking about before. And so this is just a picture. So imagine protons and neutrons in the middle here. So the strong nuclear force keeps them together versus there is a repulsive force because those protons are next to other protons. Now, say we were to decrease this strong nuclear force, remember this is one of the strongest, all the way over here, by 50%. So that sounds like a lot. So if I were to decrease it by 50%, You would think, okay, well, that's a big change, but it's really only 1 part in 10,000 billion, 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 billion. So it seems like it's a lot, but it's a very small change. Now, like I said, since like charges repel, the strong nuclear force would then be too weak to prevent this repulsive force between the positive charged protons in the atomic nuclei. So then what would happen is the proton and the other proton that's in the nucleus that normally would be okay with each other because of this strong nuclear force now is not. So now what's going to happen is they're going to repel each other. And so now our nuclei is literally going to tear apart. And so anything that has more than one proton isn't going to want to be together. They're going to want to break apart. And so all we're going to have left is hydrogen. And we can't have intelligent life from hydrogen. Maybe you've watched something sci-fi, maybe some Star Trek, and you think maybe we can have intelligent life from hydrogen, but that's not the case. We need to have more stable complexity in our elements so that we can have life. And if our strong nuclear force was too weak, we wouldn't be able to have this. So the exact precision of this 1 part in 10,000 billion, 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 billion is what allows us to have variation in our nuclei and thus able to have stable complexity and life. Our last one is the original phase space volume. So this is kind of a little more of a complex one. It's a mathematics and physics term that refers to the volume that includes all possible states of a system. So specifically, we're referring to the original state of the universe. So we're trying to think about the volume of the universe. Now, this is tuned to an accuracy of 1 part in 10 billion multiplied by itself 123 times. So to give you an idea, this precision of this number has so many zeros, like 10, how many zeros it has after the 10, that we can't even actually write it. This is more zeros than the number of elementary particles in the entire universe. So if you were to try to sit there and write it, like the other one had 53, you could write it. It would take you a while. But this one, like, it's just not, you can't do it. You would die before you did it. So this is the level of precision of this specific constant that we need to be able to have life. Now, on the second part of my talk, I kind of want to talk about some arguments regarding the anthropic principle or the fine-tuning principle. So the anthropic principle says we have all these constants that are fine-tuned. So that must mean that there is a designer. So remember our analogy of going into the biodome on Mars, that somebody must have kind of tweaked all those dials for life to exist. So there must have been a designer for the biodome. But let's talk about some other arguments that say that the conclusion that it was a designer for all of this is not the case. So we're going to talk about 4 different ones. First is random chance. Second is the theory of everything. Third is the weak anthropic principle. And fourth is the multiverse theory. Okay, so let's talk about random chance. Now, to give you an idea of, let's say you went in and you're like, oh, all these dials by random chance just happen to be turned to the right level for them to exist. That's why we have, the biodome. Or in this case, why we would have all those constants correct. But this alternative is really remote. So let me help you kind of illustrate this. So say I walked up to you and I bet you for $1,000 or 1,000 euros, 1,000 pounds, that I could flip a coin and get heads 50 times in a row. I'm like, yep, I can do it. I bet you. And you're like, all right, show me. And I do it. You sit there, you count it, and I do it. You wouldn't just be like, wow, that's awesome. You would automatically think that like either I tricked you, something happened, like the coin that I'm flipping is like rigged or something to like always land on heads, or it's a magic trick or something. Like, that the odds of that occurring are about 1 chance in a million billion. So very, very, very awful odds. So you wouldn't assume that I actually did it. You would assume there's some trick. that I'm trying to like win one over on you. Well, this is true. This is the same idea for the fine tuning of the universe. Before you would conclude that it's a random chance, you would actually conclude that it's rigged, it's designed. Someone's kind of tweaking it to end up being that way. So, this is why the random chance alternative really isn't very strong in this argument. All right, let's look at the second argument. So, this is the theory of everything. So what this theory says is that, okay, we have all these little constants in physics and our laws of nature that are finely tuned. Well, maybe there's some like umbrella principle, some, overarching principle that has kind of like caused each one of these to be a certain way. So all the parameters are the exact values they are because of this undiscovered principle. But if this were to be true, say there is some overarching principle that now caused everything below it to be fine tuned, that would actually support our fine tuning principle. Because if there was one overarching theory that was designed in a way to make all of the other ones below it, all like the dials, to be turned exactly where they needed to be, then that's even more impressive. Because then where would we get this, overarching theory from? How did that exist? So it would show that actually the designer is even more ingenious than we first thought, because it would be more difficult to create a theory or law or principle that controlled all these dials to be fine-tuned to that than to control each one by themselves. It's much easier to say, okay, I need to make this one be at this place, this one and this one and this one and this one. And then to find some way that I have some mechanism or law that will tweak each one of them overarching. So that's kind of the argument to the argument of the fine tuning to the theory of everything. Now, the third one is the weak anthropic principle. And so it's already kind of says in its name, it's weak. So it's trying to weaken the anthropic principle. So this principle states that if the universe were not fine-tuned for life, then human beings wouldn't be around to observe it. So they're saying we only see the fine-tuning because we're here. If it wasn't fine-tuned, we wouldn't be here. We wouldn't see it. So they contend that there's no explanation really required because we're here, we have it. But this doesn't really like sit well, I think. So, for example, I'll give you this illustration. Suppose you were standing before a firing squad and there's 50 highly trained military people that their job is to point straight at your chest from a very short distance and to shoot you. So they all shoot and then you're alive. Not one bullet hit you. I don't think you would just be like, oh, well, if someone had shot me, I wouldn't be here to really think about it. I think you would be really surprised and be like, what happened? Like, how am I here? This doesn't make sense. I shouldn't be here. Like, you would want an explanation and you would want to try to figure out the circumstances. So that's why this one is kind of considered the weak anthropic principle, because it just kind of says, well, we're here, we should be happy, and kind of just like not really think about it. But as scientists or as just smart human beings, we just kind of want to know. We have a curiosity, a natural curiosity to understand why we're here. And like in the beginning with those two questions from Alistair McGrath, like not only how is it that we're here, but does that reason for being here and it being so kind of surprising that we're here, does that lead to some understanding of our purpose? And I think everybody would like to know, what's your purpose, in life, and why are we here? So the last kind of argument against the anthropic principle, and this one is considered to be a little bit more of the stronger principle, strongest argument against the principle, but let's just talk through it. So this is the multiverse theory. So the argument is there could have been millions and millions of different universes, each created with different dial settings of the fundamental ratios and constants that we talked about. So many, in fact, that the right set was bound to turn up by chance. We just happened to be the lucky ones. So still kind of similar to the other arguments that we talked about. Okay, we just were here by chance, but they're kind of trying to explain why there's chance happening. So the illustration of what they're trying to say is, if I were to go in and see this like huge stack of clothes and I'm trying to find like a jacket, if I keep just trying on jackets and there's a bunch of jackets, eventually I'm going to find a jacket that fits. So this is kind of the same idea, that there was multiple universes after multiple universes. So eventually there would be a universe that would allow for life, that would be suitable for life. And we just live in that universe. But let's talk about this a little bit more in depth. So many physicists actually follow this line of thinking, but mainly as a way to avoid the fine-tuning evidence for designer. But the multiverse, and also the multiverse theory, is only a hypothesis. There's actually there's not any scientific evidence. It's kind of more an idea or a concept that has been proposed. And even supporters of this theory have just provided that there is no evidence. So we will go into it in more depth, but I just wanted to lay that out first. That right now there isn't any scientific evidence to really support this theory, this hypothesis. But let's just go with it. So for the multiverse theory, part of it is the inflationary model. So similar theory to the multiverse theory, and it's kind of an explanation of how this would happen. So if I'm just going to have a bunch of universes and we just live in the one, how are these universes just going to exist? And so this idea comes from Andre Linde, who proposed the self-reproducing inflationary universe model. So this believes that there's kind of this pre-existing superspace. It's rapidly expanding, and there's a superspace. And in this superspace, universes are kind of popping up. And they pop up because of kind of fluctuations in this inflation field. So the way you can think about it is that if you ever kind of have like dish detergent, you've got water with some dish detergent and then little soap bubbles are kind of popping up. So the super space would be kind of like the soapy water, and the bubbles that are popping up would be each a new universe. So this is kind of the idea of like this self-reproducing inflationary model. If you just have all these little universes or bubbles popping up from the soapy water or super space. So you can kind of see it in this little model in this picture. So in the chaotic inflation theory, which is part of the self-reproducing inflationary universe model, a huge number of universes are going to be randomly birthed due to these kind of fluctuations in this superspace. So at various parts in this ever-expanding superspace, that universes are going to keep popping up. Now, the reason that we need this superspace is because the superspace, which is infinite in size and endures forever, but each universe needs to have a beginning, because our universe has a beginning. It has a beginning, and we can, look at the size. So we need a theory that matches the Big Bang Theory. So each of these universes has a beginning and is finite in size. But where they come from is what is infinite. So superspace and then finite universes kind of popping out of this superspace. Now, how would this work? So let's kind of think through the many universes. If this were true, let's just say, okay, great, it's true. Does that actually mean that there's no design? So the many universes does not destroy the case for design, but actually, like I said before, if we had the theory for everything, if there was that overarching theory, that would actually support design. If the multiverse theory were true, then this would also actually support design. So why would you say it needs to point toward design? So I want to kind of compare multiverse kind of system that is there to a bread machine. So if I want the multiverse, I have to have the super space, I have to have all these things. But let's compare it to a bread machine. So if I want to create bread in my bread machine, I need a few things. First, I need the machine itself. So I need the bread machine. It's got the right circuitry, the heating element, the timer, all of that. But just having the system, the machine, doesn't matter. And then need to put all the right ingredients into the bread machine. I need to put the right ingredients in the right proportions and in the right order. So I can't just dump in, handfuls of it all. It has to be the right proportions, and there's kind of an order to it. So my milk, my flour, water, salt, sugar, yeast, all of that. And then if everything is just right, it's going to produce a loaf of bread. Otherwise, it will just be like a big clunky burnt hockey puck, or who knows what it'll look like. So if we want the bread machine to work, it has to have certain specific parameters to make the bread. So if we're trying to have a universe be made, then that machine also would be highly designed. So let's kind of compare that. So for our many universe machine, it also has a lot of factors that need to, be happening to produce this functioning universe. So first, just like I said with the bread machine, we need the parts, we need the ingredients in the right order, and all of that. But for our, multi-universe machine instead of our bread machine, this would need a mechanism to supply the energy for the bubble universes. So this is considered the inflation field, that super space, that has the reservoir of unlimited energy. So that's where we're going to get the energy. Then it would need a mechanism to form the bubbles. So this would be Einstein's equation for general relativity. Because of its peculiar form, this would cause the bubble universes to form and the ocean to keep expanding. Third, we need a mechanism to convert the energy of the inflation field to the normal mass energy that we find in the universe. So we've got the inflation field, but what we see in the universe for our mass energy ratio, it would not be the same. So we need some sort of way to convert that. Fourth, we would need a mechanism to allow enough variation in the constants of physics among the various universes. So if I'm trying to make bread and I'm trying to try it out without a recipe, I'd have to keep testing the different proportions and different ingredients. So I need something that would randomize those proportions until I kind of hit the sweet spot, the right proportions of each of those ingredients. So we need the same thing. We need something that's going to tweak all the dials to adjust them so that when the universe comes out, it's not just the same every time, that it's going to be different versions of this. And so the explanation for that would be superstring theory. So I just want to go into superstring theory just briefly, since it's kind of a hot topic. So according to superstring theory, the ultimate constituents of matter are strings of energy, and they undergo kind of quantum vibrations in 10 or 11 dimensions of space. So their shape determines the mode of vibration of the strings. And so this would determine the types and masses of fundamental particles and the characteristics of the forces between them. So this is why we'd be able to get different constants of physics and laws governing these forces based on the different types and masses and the different shapes of these strings. However, this is just a theory. It's highly speculative and there's no experimental evidence. So even though we kind of have a theory, we don't have any evidence that this even exists. All right, back to our bread machine. What else do we need? So fifth thing we need is we need the right background laws in place. So there are certain laws that just have to exist. So if we're talking about we need to tweak all the dials to be the right way, we also need certain dials to even just be on the board. If those dials aren't even there, it's not even going to happen. So the first one is the principle of quantization. So this keeps the electrons from being sucked into the nuclei. So remember I said we have protons and neutrons in the middle and electrons outside. So positive, negative. What this keeps these electrons from just sucking right down into the nuclei. The second thing we need is the Pauli exclusion principle. And this prevents all electrons from occupying the lowest orbital around the nucleus and causing complex atoms to be impossible. So if we did not have the Pauli exclusion principle, everything would just stay kind of in this lower level. But because of this, then we can have variation in the levels of the electrons in distance from the nuclei. And then that allows us to have more complexity. So we need this to have complexity so that we can then be able to have different elements, atoms, etc. And then gravity. If we don't have gravity, planets, stars can't form. And then the sixth thing we need is the cosmological constant. And so remember, we said that that guy was very, very precise. And we need it to make trillions upon trillions of universes. And so if we want him to be precise, remember I said that he was very, very precise number. It would take, if we were like, okay, let's see if we can just get the cosmological constant correct, we would have to just keep pulling out trillions upon trillions of universes to come with at least one universe with this correct number. And even if it has this correct number, that doesn't mean that all the other numbers on the dials would be correct. So just trying to get this one that we have to have correct is going to take trillions upon trillions of universes. So what that means is if we were to have a many universe machine, this machine, this universe generating machine, would have to be very, very, very well designed. It's going to be way more complex than that bread machine. And so even if this were to be true, this would just increase our explanation of design. Because for a many universe generating system to even exist, it would require even higher level of precision and design than even the theory of everything. So even though this one and the theory of everything are supposed to kind of combat the anthropic principle, it really it just kind of brings up the design a level higher. So anthropic principle says the design is here. Excuse me. At this level. If we were to have the theory of everything, it just brings the design level up a notch. If we were to have the, multiverse theory, this universe generating system, machine kind of thing, then it would be even higher. So if these things were to one day, we have evidence saying that they exist, it does not defeat design. It actually just provides even stronger evidence that design is actually the case. All right, so this is our talk on the anthropic principle or the fine-tuning principle. Here are some references, just a few of them to get you going.